Once again, happy Movember. In this video on some IB quantum mechanics, topic 13, we're going to do some crazy stuff like the Schrodinger wave model of the atom, and then Heisenberg and some uncertainty, and then we'll even talk about how you can kind of estimate the radii of some nuclei based on the way things scatter. Using Bohr's model of the hydrogen atom, scientists were only partially able to explain some of the energy levels they were seeing and some of the mathematics. So then this guy Schrodinger, an Austrian guy, comes along, and you may have heard of him before. He's well known for Schrodinger's cat, which is an interesting story, but something a little bit different. But this is Schrodinger, right over here, and he came up with this wave model. And then this guy Max Born later adapted it and made it even a little bit better. And kind of the main gist of what Schrodinger was saying. Maybe you guys want to pause it and read all of these features here. Now the main thing is that he said the electron, let's not think of it as an actual particle that you could actually pinpoint and say is going to be at any one spot. Instead, let's think of it as a wave, and it's kind of everywhere at once. And he said, if we give this an equation, he called this psi, which was like the probability density, and then Max Born came up with this psi squared equation that allowed you to determine, at least you could know a probability. And so instead of your nucleus, and you've got like these orbitals, like planets, instead, they said if it's a wave, and you can't ever tell where it is, let's think of things more as like an electron cloud. And this wave equation is going to tell us kind of about where there's a good probability of that electron being. And the mathematics, which are complex and beyond the scope of this course, the mathematics tended to work out well. And even though it's sort of a crazy idea, people are like, oh, this Schrodinger guy, this Born guy, they're kind of smart. In the 1920s, this guy Werner Heisenberg here, he's a German guy, at the young age of maybe 28 or something, he decided, oh, I guess I'll revolutionize quantum physics, and came up with the idea that if you're trying to measure something incredibly small, like an electron, he said that you can't actually know simultaneously its position and momentum without a little bit of uncertainty. Let me move this principle by him on here. Maybe pause this, write this down for a second. If you want to think about why that might be an actual fact of nature, which it turns out it is, think of if you've got an electron and you want to measure exactly where its position is. So maybe you're going to use some very small wavelength radiation and bounce it off this electron. Well, if you do that, the electron is so small, you're going to knock it somewhere and you're going to change its momentum while you're trying to exactly know its position. So any measurement that happens is going to affect one of the other variables, and so it becomes a fact of nature that you can't know these things exactly. And if you want to look at this in equation form, if you're looking at position and momentum, you can say that this is true, where its position, or its uncertainty of position, and its uncertainty of momentum, those have to have a certain minimal value, and both the product of that has to be greater than our old friend Planck's constant, I think I spelled that wrong, but that's okay, divided by 4 pi. And another form of this is that you can also think of it in terms of time and energy uncertainty, also have to be bigger than Planck's constant over 4 pi. And this had some interesting effects because previously your strict Newtonians were deterministic, and they said, well, if we know exactly where anything in the universe is, and we know and understand the laws of nature and gravity and force, then we should be able to predict where everything is going to go, and that means that the whole universe is already predetermined and there's no free will. And here Heisenberg is saying, well, no matter how well you know the laws of the universe, there's always going to be some uncertainty, and so the universe can't be predetermined. At least maybe that's not what he said, but that's kind of an interesting relation to what this is all about. Fortunately, like much of the math in this Topic 13 unit, the math turns out to not be very difficult, as long as you understand what in the world they're asking you to do. So here's a IB style problem, and take a minute and read it and pause it and see if you can solve it. Now, we're going to start with Heisenberg uncertainty principle. That says the uncertainty of the momentum in the position has to be greater than Planck's constant over 4 pi. And they're telling you the uncertainty right here. So what you want to do is solve for position. And then you just fill in your numbers. Planck's constant is going to be, and then you're going to divide that by your 4 by pi by your uncertainty of 0.01 times 10 to the negative third meters. And then when you solve that, you're going to get a change in moment, or that the momentum has to be bigger than, I believe I'm getting 5.3 times 10 to the negative 30th kilogram meters per second, because it is momentum. Now you could have, even if you wanted to, put in half of this, if you think the uncertainty is only half of that. The IB is pretty lenient in this realm, because we're dealing with some tiny, tiny numbers. Just want to be of the right magnitude of 10. And then, in this second part, what direction is the component of the momentum? And this answer is, in this case, vertical or perpendicular to the beam direction. Because since you have that vertical spacing there, you have some play on which way the momentum of that electron could be going. If we look at some of the experiments that we've talked about before, such as the Rutherford gold foil experiment, which is the same thing as the Geiger-Marsden experiments. It was a scattering experiment because they were firing these alpha particles at atoms, and then they would scatter and go these different directions. Now what's nice about this is that allows you to, if you look at the closest distance that those alpha particles can approach, that's going to let you know the radii of the nucleus, or actually how big a nucleus actually is. And the way that we do that is we say that it has a certain kinetic energy, this alpha particle, and it's going to slow down because it's being repelled by this nucleus. It's going slower and slower, and that kinetic energy is turning into potential and more potential and less kinetic, and eventually it stops and it's all potential energy, and then it goes zing and it goes flying the other way, and the potential turns back into kinetic. And the mathematics that let us figure out the closest approach is that we can always say that the kinetic energy is equal to the electrical potential energy. And this Ke is equal to the electrical potential energy of a point charge, which is going to be K Q1 Q2 over R, where this Q1 might be the charge of the particle, and Q2 might be the charge of the nucleus. Now repeatedly, the only type of problem I've seen the IB ask related to this is calculate the distance of closest approach, or calculate the minimal radius size of a nucleus. It's basically the same problem. And here they're saying that's fired at gold, and they would have to tell you that gold has 79 protons in it, and this alpha particle is zipping in with this 8.2 mega electron volts. First step, well, take a minute, pause it, try and solve it. First step, you have to convert the mega electron volts to joules, and if at this point in time you don't know how to do that, you need to take a good hard look at yourself, because all you're doing is saying that 1 electron volt is equal to this many joules, and you do the conversion, and you're going to get something like 1.3 times 10 to the negative 12th joules, a tiny amount of joules. And then you set this energy, which is kinetic, equal to the maximum electrical potential it has when it stops, right when it's about to bang into the nucleus. And that's going to be K Q1 Q2 over radius of the nuclei, or maybe just beyond the radius of the nuclei. You fill in your numbers. This is going to be about 9 times 10 to the 9th. Q1, maybe that's going to be our gold nucleus, 79 times 1.6 times 10 to the negative 19 coulombs. And then charge of an alpha particle, you should know, has 2 protons, also times our elementary charge here. And then the R is what we don't know. Then you do the math, and that's a big hassle, because there's all sorts of big numbers. But once you figure this out, you should be getting something close like 2.7 or 2.8 times 10 to the negative 14th meters. And it turns out that that is just a little bit bigger than what the actual radius size is. If you fire that alpha particle faster, then it gets a little bit closer.